Alright, so we are still in chapter 5, practicing Lewis structures some more. We're not even quite halfway done, but let's keep on going here. So if I ask you to draw the Lewis structure of O3, which is ozone, you of course calculate the number of valence electrons. 3 times 6, oxygen has 6 valence electrons, gives us a total of 18. It's easy to decide which goes in the center because all three are oxygen, so we just put them in a row, which uses up 4 electrons, and then you distribute the remaining electrons from the outside to the inside, and you stop when you have reached an octet. So we have 4, 6, 8, 10, moving on, 12, 14, 16, and then moving to the inside, going to 18. We're done. You should recognize right away that the one in the center does not have an octet, so one of these lone pairs here is gonna have to make a double bond, right? So you are always gonna move a lone pair from an atom that has an octet to make a double bond, because it doesn't matter whether this lone pair belongs to the oxygen exclusively or if it's shared, right? So it gets to keep its 2 electrons, whether it's a lone pair or it's shared. So then we get a Lewis structure that looks like this, and this is the best representation of that particular element, ozone molecule. And there's a resonance structure because we can also make a double bond on the left side. And so you can, if I ask you to, you can draw that. And those are chemically equivalent electronically, right? There's no difference between them. All right. And so those are called, again, these are called resonance structures, right? And so what actually happens here, there's an electronic driving force, which we will talk about in a minute, that wants to push this electron density back away from the oxygen, okay? So, and as it does that, the oxygen in the center cannot handle another double bond, so that pushes the electrons back out here. And then once it's here, it's going to do the same thing. That oxygen does not want that extra electron. And so we've got a constant push back and forth between those three, okay? So these electrons are delocalized. And you would normally say, if you look at a single structure like that, you would say, okay, so there's a double bond here and there's a single bond here. This is called, or referred to as, a bond order. The bond order between these 2 oxygens is 2, and the bond order between the other 2 oxygens is 1, okay? At least the way it's drawn. But the reality is that these 2 electrons go back and forth so fast that the bond order that is measured is actually 1.5, right? So those 2 electrons are distributed evenly and they move very fast. And one more thing, this is really Vesper theory, but it makes sense, and it's good to point it out at this point, right? So this lone pair stays put, it doesn't move. It's really the lone pair on the outside oxygen that, and the lone pair, the bonded pair here, the bonded 2 electrons that are moving back and forth. So this thing stays put, right? And it takes up space, right? Electrons take up more space than atoms. So this is going to push down, so its actual shape is going to be bend. Okay? And these electrons are distributed evenly. So it would be a better representation, or this is a more informative representation here. Okay, so here you have a clear-cut bond order that's 1.5. Now, of course, I'm going to ask you to draw a single representation. So you want to draw either this one or that one. They're both equally contributing to the ozone. Okay. So let's talk about some molecules that have exceptions to the octet rule, right? So there are some compounds that are radicals. See, they have an odd number of electrons. Okay, they're rare. And they're highly reactive, so they don't stick around very long. But if you look at NO, nitrogen has 5 and oxygen has 6, so that's 11. You're never going to be able to pair all them up, and you're never going to be able to fulfill the octet rule here, right? So we'll draw this in a minute, but this is both an exception to the octet rule as well as contrasts or indicates that we can have an odd number of electrons for some molecules. And then there are some, and I mentioned both of these already, that can have fewer than 8 electrons and are perfectly happy. Hydrogen only has one quantum level to fill with 2 electrons. So it is the ultimate exception. It's going to just dangle off to the outside with a single bond. It's never going to have double bonds or more than 2 electrons. It will always be terminal like this. And boron can have 6, can be stable somewhat or happy, such as BH3. Again, we're using H as an example here for being terminal and only having 2 electrons, and in this case also the central atom has only 6 electrons. Okay, and so boron and hydrogen are the only 2 exceptions there. But I also told you that you can have a donor bond, right? Something like nitrogen, ammonia can come in and donate that electron density to the empty p orbital. Okay, and then you get 8 electrons for everything. And finally, you can have more than 8, but only for the second period and below. Like PF3 has 5 bonds, and then SO2, as we will revisit in a minute, can have more than 8 electrons. Okay, so what are we talking about here, and why is that? We will re-emphasize that when I talk about valence bond theory, but for now, you need to understand that this row, the second row here, they never do that. Okay. In fact, we know boron can have fewer than 8, and carbon, nitrogen, oxygen, fluorine, they are always going to have 8, no matter what. Okay, and that is because you have to put these electrons somewhere. They have to go into an orbital. Okay, and since here energetically all we have is one s orbital and 3 p orbitals, that means we can only accommodate 8 electrons. In order to put 10 and 12, you're going to need another orbital. And so for these, you can either use the 3s here, in theory, if nitrogen wanted to do that, okay? It would have to use the 3s or the 3p. But the energy of those orbitals is just too high. Remember that n equal 1 was down here, and then n equal 2. There was a rather large energy difference, and then n equal 3, there was a shorter gap here, but still it's too large for the second period elements to populate those high energy. It just is not energetically favorable. Now what happens when you have phosphorus, silicon, sulfur, you actually are approaching low-lying d orbitals. Okay, so you can actually use the d orbitals to make 5 and 6 bonds, right? So you are, and these are all empty. The 3 d orbitals for these elements are all empty. And selenium then of course is going to use the 4d elements, the 4d orbitals, which are also empty, to put those electrons to make an expanded octet. Now this will all make more sense once I talk about valence bond theory, but it's good to throw out already. And so a little side note here, you know, if you've ever seen a sci-fi movie from the 80s or something, and sometimes you hear references about silicon-based life forms, right? So, and silicon and carbon, as far as bonding is concerned, are actually drastically different. Carbon makes double bonds and triple bonds. Silicon will not. Carbon will always have 4 bonds, and they bind to each other very nicely, and silicon can have 5 and 6 bonds. Okay, so they're drastically different, and so any organic or silicon-based life form would have drastically different structural molecules, and their DNA would probably be completely different, and it wouldn't be DNA, it would be something else. So just a little side note here. Okay, so next we're going to talk about a formal charge. And this is going to be the driving force that pushed the electrons from oxygen back to the double bond, if you remember, just a minute ago when we did O3, right? We did O3. And I told you that there's an extra electron there, and you can determine that by calculating or determining the formal charge. Okay, that's not to be confused with a partial charge, which comes about polarity, right? So here we have water. We already know there's a difference in electronegativity. We have polar bonds. This is a polar molecule. So these are partial charges. They're not formal charges, okay? Okay. Whoa. this is of course plus, this is negative. Oxygen is the more electronegative element. It draws electron density towards it. Okay, so now let's take water. Oh, not quite yet. I have to give you the formula first. But we can also calculate the formal charge, right? So sometimes electrons are not shared equally. And it will also tell you when you need to go beyond the octet, right? Sometimes you need to make 5 and 6 bonds to relieve that formal charge. Okay? Right. Hey, let me go back to this statement here. Just emphasize that. It'll determine the proper Lewis formula or structure, right? So the structure will change. The formal charge, and we're going to do water, and we're going to do ozone. And then we're going to do a bunch more all together, of course. All right. And I'm having a lot of fun. I don't know about you guys, but this is a hoot and a half. Okay, so a formal charge will be calculated for each atom in the structure, and you will have to do that if I ask you to, and in order to decide if the structure is good. All right, so let me put those 2 electrons back on oxygen. That's the proper Lewis structure. Now, the formal charge is calculated by taking the valence of the atom. So let's do hydrogen. Hydrogen has a valence of 1. You subtract half of the bonding electrons. Here, these are electrons. Okay, so there are 2 bonding electrons. Half of it is then 1 minus 1. And minus the lone pair electrons. Okay, hydrogen doesn't have any lone pair electrons. So 1 minus 1 minus 0 equals 1. Sorry, 0. There's a formal charge of 0 on both of those hydrogens. And that's good because that's what we're looking for. Oxygen has a valence of 6, right? The valence is the same thing as the valence electrons. If you think about it, right, they're kind of like valence protons, right? So there's this positive 6 charge there that dictates that we have 6 electrons on the outside, right? So there's no such thing as valence protons, but it's just maybe to help you figure this out, right? So, and then if you have more than 6 electrons on the structure, you get a negative formal charge. If you have fewer than 6 electrons on the oxygen, you have a positive charge. So that's kind of what it's looking for, right? So you're looking at that, right? So, but oxygen has a valence of 6. There are 4 bonding electrons here. So half of that minus 2, and then 4 lone pair electrons. So again, that's a formal charge of 0. So this is what we want. So in a way, what you're looking at is you're looking at the electrons that are on the oxygen directly here, right? So here you have 6. Right, this one is too far away. It doesn't affect the formal charge, right? So this is essentially what you're looking at, right? So this is good. Everything is 0. Now let's do the same thing here for this oxygen, for each of these oxygens in ozone. So here we have a 6 minus half of 4 minus, which is 2, sorry, minus 4, which is 0. So this has a formal charge of 0. Okay. This one has a valence of 6. It has 3 bonds, so that's 6 electrons. Half of that is 3, and it has a lone pair. So 6 minus 5 is plus 1. So this oxygen actually has a plus 1 formal charge. This one has 6 minus 2 over 2 minus 6. So this is minus 1. So, and this has a minus 1 charge, right? So if you add up the formal charges, this is something else that's good to know. You should end up with the charge of ozone, right? Ozone has no charge. O3 has no charge. So minus 1 and plus 1 is 0. So if you ever come up with a charge that doesn't equal the charge of your polyatomic ion or your molecule, then you didn't do the valence electrons correctly. So it's kind of a nice double check. But this is exactly why these electrons are delocalized. This oxygen would rather be 0. So this oxygen is going to try to make a double bond and push these electrons away from it, which would relieve this charge to be 0, right? That's what it's after. So you always want to minimize the formal charges. That's the name of the game, minimizing the formal charges. But oxygen doesn't have an empty d orbital. It cannot have another double bond, which pushes this electron density back out, creating a -1 charge on the other oxygen. So this goes back and forth. That's that driving force. But if I replace that oxygen with a sulfur, for example, you could actually have two double bonds, and you could have 10 electrons on sulfur because it can populate the low-lying d orbitals with electron density. Okay, so let's practice everything together now, right? So here we have 4 plus 6 plus 2 times 7, which is 7, 14, 20, 24. 24 valence electrons, right? Okay. And I'll tell you something else. If you're good at formal charges, you don't need to count the valence electrons anymore. All right. But let's take it one step at a time. For now, I bet most of you need to count those valence electrons and take it easy. Right. So we have a carbon as a central atom. It's the most electropositive. 2 of the chlorines are sticking out, and you have an oxygen that's hanging up there, right? So that's 6 electrons, and we're going to put in 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And then we need to move 1 down here. I'm just going to do this because I'm lazy. I'm going to erase those. All right. So that's great. And we are really done. However, if I ask you to calculate the formal charges, because carbon cannot have an expanded octet, so you don't really have to worry about formal charges at this point, but we can practice that, right? So chlorine is in group 7, so it has a valence of 7. It only has 1 bond, so that's 1 electron. And then it has 6 lone pairs, so that's -6. So it has a formal charge of 0. All right, so both of those chlorines are identical. Moving on to that carbon. Carbon has a valence of 4. It doesn't have any lone pair electrons, but it has 4 bonds, which means it's 8 electrons, so it's 8, half of 8, and that gives me 0 as well. So this is a formal charge of 0. And oxygen has 6 minus 2 minus 4, which is also 0. So this is good to go, but you can calculate these formal charges like that. All right, moving on to a radical. Okay, I was hoping to do something that actually has an expanded octet, but coming up, hold my horses, right? Okay, so this has 11 valence electrons, 5 plus 6. And it's going to be, you cannot have an octet, right? So you put the nitrogen, put the oxygen, that's 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you put this here, 11. Okay. So the only thing we can do is we can make 1 double bond here, right? So oxygen has a formal charge of 0, and nitrogen has a formal charge of 0 here too, because it's 5 minus, oh, never mind, God, okay. So oxygen obviously is -1, right? So it's 6 minus half of the bonding, minus the 6 electrons. Sorry about that. Obviously, a singly bonded oxygen with 6 electrons is always going to have a -1 charge, which means this is going to have to be a +1 charge. So let's do that. 5 minus half of 1 bond is 1 minus 3. Okay. So that's going to be +1. All right. It also doesn't have an octet. It has 1, 2, 3, 4, 5, right? So the best we can do is we can make 1 double bond. So nitrogen, double bond, oxygen, which reduces the formal charges, and that's a good thing. But it doesn't put an octet on nitrogen, right? So this one has a formal charge of 0 now, and this one is 5 minus 2 minus 3, which is 0. So both of those, so that's good, but it still doesn't have an octet because nitrogen here has 4, 5, 6, 7 electrons. So it is electron deficient, and it is reactive because of that. I already mentioned this. You have to reduce the formal charges. You want to choose the formula or the structure with the lowest magnitude of formal charges, right? Okay, all right, well, let's take a look at this molecule here. Here we have sulfur, which is 6, oxygen is 6, and chlorine is 7, so 2 times 7, so 2 times 7 is 14, plus 6 is 20, so that's 26 valence electrons. Put sulfur in the center, put an oxygen out here, 2 chlorines, that's 6 electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Well, I need to put 2 more, so I have no choice but to put it down here on the sulfur. Okay, this is actually a pretty good example. If you calculate the formal charges now, right, chlorine has a valence of 7. And I'm going to do this, and then you need to practice that so I don't spend too much time talking. All right? Minus half of the bonding is 1, minus 6 is 0. So this is 0, this is 0. If you look at oxygen, oxygen has a minus 1 formal charge, right? 6 minus 1 minus 6 is minus 1. And sulfur here has a valence of 6. It has 3 bonds, so that's 3. And it has 2, so that's plus 1. Okay. Since we are dealing with sulfur, we can actually get rid of that formal charge by moving this lone pair. You couldn't do that if it was a second row element, but sulfur has empty d orbitals. It can make a double bond and have an expanded octet. So now we're going to make an expanded octet. We're going to have sulfur with a double bond. It still has that lone pair and the 2 chlorines. So this also affects, well, the double bond doesn't affect the shape, but the lone pair does. We'll talk about that later. Anyway, forget I mentioned shape. All right, so now the formal charge is 0, 0, 0, and 0. So this is clearly the better structure. You want to reduce the formal charges. This is a reasonable structure, but it's not the best structure because there's this electronic bias. And see, in this case, the electrons don't have to be pushed out because sulfur can have an expanded octet, right? So we have 1, 2, 3, 4 bonds. That's 8 electrons plus the lone pair. That's 10 electrons on sulfur, which is okay, and you have to remember that it's okay for sulfur. Let's do these 2 and then take a break, right? These 2 I already drew, but we have to consider formal charges now, right? So we have sulfur, and I drew it like this. So sulfur has 6, so that's 12 plus 2, and we ended up with this structure here, if I remember correctly. And so let's calculate formal charges. So this is minus 1 and this is minus 1. Well, in this case, I tell you what, you can actually not do much about that because those negative charges are going to stay. Okay? So we'll just leave that one alone. And SO2, we drew like this. We had 1 double bond and a lone pair. See, this is like ozone. And except now when this pair pushes to make a double bond, it stays. Because sulfur can do that. So that's the big difference. Now all the formal charges are 0, 0, 0, and you can do that. This has 10 electrons, and it can have an expanded octet. Okay, so we're going to look into, oh heck, I'll do one more and then I'll do Vesper theory. Alright, so let's do one more. You can pause and get a drink or something and then come back, but I just have the one left, and so I want to finish it. Alright, so sulfur is also an example of a central atom that will have an expanded octet, right? So sulfur, oxygen, all of those have 6 electrons, so 5 times 6 plus the 2 from the charge. 5 times 6 is 30, plus 2, that's 32 valence electrons. Put the sulfur in the center, and I'll do this pretty quickly here. Without much explanation, you should be able to do this. Once you're done spreading out all the electrons, you actually will have created a structure that fulfills the octet rule, right? So everything has an octet here. You've used up the correct number of valence electrons. However, you have a formal charge of -1, -1, -1, -1, and +2, right? So this adds up. +2, -1, -1 overall has a -2 charge, which is what we expect. So I counted the number of valence electrons correctly. Because sulfur is the central atom, 2 double bonds will be made. All right, I have that on the next slide for you. It looks cleaner. It shows I don't have the formal charges here. Just put them in. And you reduce that, and it doesn't really matter whether you do them across or side to side. When we look into Vesper theory, I'll bring this back up. Okay? Oh, heck, let's do one more. HCN. I'll just draw it. There you go. Done. And, oh, that's enough. I'll see you in the next lecture.